We present a method for handling realistic uncertainty in game-theoretic planning frameworks. Our method uses a feedback game structure to account for interactions that naturally arise in multi-agent settings. Consider this driving scenario, in which an autonomous car, referred to as the ego agent and shown in blue, is using a game-theoretic planner to generate motion plans. The ego agent maintains multiple hypotheses about the intentions of other agents on the road. In this case, it is believed with probability 0.2 that the red agent will change lanes. Since the ego agent is unsure which hypothesis will be realized, we propose duplicating the red agent in the dynamic game, representing both hypotheses. One version will stay in lane, and the other will change lanes. Zooming out, trajectories for the non-ego agents might be as seen here. A question arises, which is how the ego agent should consider both hypothesized trajectories of the red agent. Avoiding collision with both candidate trajectories could be overly conservative, especially since there is a relatively low probability associated with the lane change. Our method allows incorporating the probability of a hypothesis in a natural way. When the probability equals 1, the ego agent completely avoids the desired plan of the hypothesized agent. When p equals 0, the ego agent ignores the hypothesized agent. Intermediate probabilities interpolate these two behaviors. To accomplish this, we introduce a novel formulation of the constraints and objectives appearing in dynamic games. The non-ego agents nominally are responsible for collision avoidance with the ego vehicle. However, by increasing the parameter p from 0 to 1, the responsibility of satisfying this constraint is effectively transferred from the non-ego agent to the ego agents. We apply this idea as a tool to handle uncertainty in the intentions of other agents in the scene. For every hypothesis regarding the intentions of other agents, we duplicate that agent and assign collision avoidance responsibility based on the probability associated with the corresponding hypothesis. Consider the example from before. Visualized here are 3 different solutions to the dynamic game, each corresponding to different probabilities associated to the lane change hypothesis. As expected, when p equals 1, the ego agent slows considerably in anticipation of the lane change. When p equals 0, the ego agent continues to pass at its nominal speed. Here's another example in which the ego agent is attempting to change lanes. It maintains uncertainty about how fast the approaching red agent is traveling. The more certain the ego agent is that the red agent is traveling very fast, the more it accelerates as it changes lane. As a final example, consider the scenario in which the ego vehicle is changing lanes in front of the red agent, of which the nominal speed is unknown. The green agent in the far lane may also change lanes. Based on the probability of these independent possibilities occurring, various behaviors naturally emerge. The method we present relies on modeling interactions as a dynamic feedback game. Since established methods for solving constrained versions of these type of games do not yet exist, we developed a custom solver for the purposes of this work. We believe that solving games of this nature is possible in real time.